This program is brought to you by Stanford University. Please visit us at stanford.edu.
Good evening, everybody. I'm Charlie Junkerman, Dean of Continuing Studies, and it's a pleasure to see so many of you here tonight. I just want to say what a pleasure it is to start. In fact, we've been looking forward to this for 9 months, planning, thinking, conceiving, inviting, and today's an exciting day for those of us who have prepared this for you, and we hope it's the beginning of an exciting 10 weeks for all of us. One of the motivations for this course is that this is the 20th anniversary of Continuing Studies at Stanford, 2008. We're very young, and we took the opportunity to piggyback almost on a bigger anniversary for Darwin, both the bicentennial of his birth and the 150th anniversary of the book, The Origin of Species, which has fundamentally changed the way we think in almost every discipline of human thought. People in Continuing Studies, I and my colleague Azim Massoudi, floated this idea with Bill Durham, his colleagues Bob Siegel, Carol Boggs, and others, and we were delighted that they were bit by the same bug of enthusiasm as we were, and we started working hard to put this together. It's in many ways an extraordinary experiment. One, as you can tell, it's a hybrid course blending undergraduates and continuing studies students. Two, it's extraordinarily interdisciplinary. There are representatives in this course from 9 or 10 disciplines, depending on how you count. It has a cast of 31 characters, and you can imagine the logistics. 31 discussants and presenters, many of them coming from outside of Stanford. So it's going to be rich, it's going to be exciting, it's going to be diverse, as it should be in a Darwin course. What else makes it extraordinary? It's being videotaped for upload on iTunes. That's why we have these bright Hollywood lights, the cameras, and microphones in the aisle, which Bill will explain to you briefly. Many of you go to Stanford iTunes and download things. Courses that we put up on iTunes regularly are downloaded between 400,000 and 500,000 times, which is just remarkable to me. Given the big anniversary coming up in 2009, I'm sure this one will be downloaded even more. So it's extraordinary in that way as well. Finally, it's huge. Here we are in Cubberley. It's not where we planned to be. We planned to be over in the geology corner, but we had to move. None of this would have been possible without the collaborative enthusiasm of the people on the planning committee, whose names I've mentioned, and the financial support of Stanford's provost, John Etchemendy. Our biggest debt is to the person whom it is now my pleasure to introduce, Bill Durham. Bill is Bing Professor of Human Biology, Professor of Anthropology, and Yang and Yamasaki University Fellow. He's a winner of the prestigious MacArthur Fellowship Prize and came to Stanford in 1977 after finishing his PhD at the University of Michigan. His main research interests are in ecology and evolution, the interaction of genetic and cultural change in human populations, and the challenges to conservation and community development in the Third World. I just get tired reading this, Bill. During his tenure, I'm not going to do the big thing. I'm just going to be short, but even that makes me tired. He's received the Gores, Dinkelspiel, ASSU, Rhodes, and Bing Fellow Awards for his teaching. I'd say that's a clean sweep. His work has been supported by the National Science Foundation, the Guggenheim Foundation, the Danforth Foundation, and the MacArthur Foundation. He's been a fellow at the Center for Advanced Study in Behavioral Sciences, right up on the Hill, served as Director of Human Biology and Chair of Anthropological Sciences at Stanford, and as editor of the Annual Review of Anthropology. And as some of you know who are here in the audience, he is one of the most popular people to go on trips with. And I know a number of sophomores and alumni in the audience here have just returned from the Galapagos with him. And it's also the case that on the very last day of this course, he's going to take a red eye to Tanzania to follow the route of Darwin's beagle, 30-some day trip. So in between the Galapagos and Tanzania and the route of the beagle, we get him as the leader of our 10-week journey. Please welcome Bill Durham.
Thank you and welcome to all. This is an exciting moment for us, almost a dream come true as we began to ponder the idea of this class just about a year ago. Darwin's Legacy is a course on the impact of evolutionary thinking on the social sciences, the natural sciences, and the humanities. And it's my job tonight to do a brief introduction. You'll learn right away that anthropologists aren't real great with numbers, because I want to begin by congratulating for what I thought was 25 years of terrific courses and educational opportunities. For 20 years of terrific courses and educational opportunities, we say thanks and congratulations to Dr. Junkerman and Continuing Studies. We are just so very pleased to be sharing in that celebration, and what a great kickoff to an entire year of Darwin bicentennial events. Let me explain who the we are, who were involved in congratulating Charlie and putting this course together. The Darwin's Legacy Planning Committee, a group of dedicated evolutionists, as Charlie mentioned, included Dr. Carol Boggs, professor of teaching in biology and director of the program in human biology. Dr. Rodolfo Dirzo. Rodolfo, stand up this evening. Bing professor in environmental science and biology. Dr. Charlie Junkerman, whom you've just met, associate provost and dean of the Continuing Studies and summer session. Dr. Robert Siegel. Bob? Good evening. Associate professor teaching of microbiology and immunology. Look at all the teaching that's up on that list. You can see the priority of the faculty here. We want to make sure this is a carefully taught course, and myself in human biology and anthropology. In addition, we have the wonderful assistance of Azeen Masoudi. Azeen, would you stand? Hello, Azeen. Maybe she stepped out. She's probably arranging things for us after the class. She's the events and communications manager at Stanford Continuing Studies. And we have a very talented and experienced TA. Joe, are you here? I know he went off. Where's Joe? There he is, way in the back. And since you can't see him in the darkness, I'll show you a picture taken in the Galapagos just a week ago, where Joe was also traveling with us in Galapagos. I'd like to identify four main goals of this course. First, to celebrate Darwin, and perhaps even more importantly, to celebrate evolutionary thought. The impact of a line of thinking, of a philosophy of science, an evolutionary philosophy of science. 2008-2009 is the bicentennial year, as we've mentioned, of Darwin's birth, plus it's the 150-year celebration. Since Darwin was 50 when he wrote On the Origin of Species, it follows that this is the 150-year celebration of On the Origin of Species. There'll be lots of other events and activities at Stanford, including a Darwin Festival Day in February, because February 12th is the birthday. But with this, we're off to a good start. If you go, in fact, to the Darwin Online website and look at the world events planned for 2008-2009, you'll notice that ours is perhaps the grandest of all the starts. As you know, we're celebrating 200 years of another important figure born on the same day, and I really got a chuckle out of Newsweek this summer. The Mostly Big Thoughts edition. Unfortunately, they kind of put it, Lincoln versus Darwin, who matters more? And I said to myself, wow, talk about apples and oranges. A classic example. What's the point of who matters more in that one? Fortunately, in this class, we're simply going to focus on Darwin and explore the Darwin side. Darwin's idea of evolution by natural selection has been called the single best idea ever, at least in this book by Amanda Chesworth et al., and we'll be asking, why is that the case? The single best idea ever. Why would we call it that? A second goal of this course, to explore the reach and impact of evolution in the wider domain of scholarly thought. The social sciences, including psychology and anthropology, we'll hear from. Humanities, including philosophy and literature, we'll hear from. Natural sciences, including paleontology, neuroscience, medicine, and biology. For everything we've included, there's at least something important left out, regrettably. Oh, we agonized over this. We thought long and hard over the many areas like geology. Of course, Darwin started his career as a geologist. How can you leave geology out? But if we took geology, put geology in, something else would pop out. Primatology, human origins, etc. We weighed many variables as a committee and did the best we could to show the full reach of evolutionary thought in a simple 10-week program. Our third goal. We have a big problem of evolution literacy today in the US of A. And perhaps we can help with that via the ripple effect, by the enthusiasm of each and every one of you and your communities and your worlds, or at least we can do our part about that. 50 then fewer percent of US citizens accept evolution as a statement about the history of life. I'll show you the data. Many don't know what evolution means, and I'll show you some data on that. So here's the results of a study done for the New York Times by John Miller at Michigan State. The acceptance of evolution as a percent of a population sample in all of these countries across the world. And here's the 50% line. Starts with Iceland, Denmark, Sweden, France, Japan over here on your left. And look at the United States of America. Snuggled among places known for free thought. Bulgaria, Lithuania, Latvia, Turkey. It's embarrassing to be registered at that place. In a study of Stanford students in 1999, Tina Bhargava, a human biology honors student, did a magnificent thesis project. Knowing that students would be standing in long lines at the bookstore, she went in with a questionnaire and asked them, do you think the modern theory of evolution has a valid scientific foundation? Ooh, 80%. All the ones with a shaded blue there said yes. Some said yes, but it can't be tested. Some said yes, it can be tested. Some said, yes, there's great support by the scientific community, so on and so on. What's interesting, though, is she went on to ask, which of the following best agrees with your conception of the modern theory of evolution? Purposeful striving toward higher forms by almost a quarter of the student body. Strong, eventually eliminating the weak by 36%. Over 50% of the Stanford students in 1999 cannot give you an adequate definition of evolution. You know we have a problem. All organisms related by descent is a winner. Human evolution from ape-like ancestors, well, that's a little anthropocentric, but if we're generous with our scoring here, wow, we're trying to give extra credit when we can. And the result is there's this thing in our country, and only, insofar as I can tell, in our country, not in Europe, not in Canada, not certainly in South America, what's called the Evolution Wars by Time magazine. With literacy so low in the United States, people are confused about directional change in living organisms without some kind of a director, and thus invoke supernatural causes. So one of our goals is going to be to clear all that up and to contribute, we hope, to the settling of this evolution war. Our fourth goal, fourth and finally, is to bring in the best and the brightest that we possibly could to share enthusiasm and perspective on Darwin. For example, next week we have Dr. Eugenie Scott, who's the director of the National Center for Science Education, a specialist on the topic of evolution and religion. And as they say, she wrote the book on it, a book indeed that we'll be using in the class. Notice that the foreword is by yet another of our speakers, a prolific writer himself. The week after that will be Janet Brown. You'll notice that most weeks our speaker wrote the book on it. Janet's got a couple of them. She's the leading biographer of Charles Darwin. She's got a two-part series called Voyaging and the Power of Place. Fabulous reading. Each one of them is about like this. Janet could speak every night for a month. Following Janet, we have Dan Dennett. What a character, what a wonderful speaker. Peter and Rosemary Grant, the famous people who've worked on the Finches, and we're just getting started. So we're in for a wonderful fest, as it were, of evolutionary thought. A few housekeeping details at the start. After tonight, ground floor seating will be reserved for registered students. That includes continuing studies, undergraduate and graduate students. Guests are invited to use the balcony up above. I know there'll be people who want to come and hear certain speakers, and we invite them to use the balcony. Undergraduates and graduates, there are two ways to enroll, Anthro 163D or Human Biology 184. There's a 3-unit or 1-unit option. The requirements are fully specified in the syllabus, so we needn't take your time with that here. But let me emphasize that sections are required for the 3-unit option. They are Tuesday or Wednesday evenings at 7 o'clock. See coursework for sign up and for details. Sign up for those sections will start on Wednesday of this week. A few more details. Undergraduates enrolled for 1 unit. A reminder that attendance is mandatory. Be sure to sign in each week. We'll have a sign-in system. Everyone, we invite your questions each week during the panel that follows the main speakers. So we'll assemble after the speaker at the table, and there are microphones in the aisles, as Charlie was mentioning, that will pass among you. Please use the aisle microphones so that everyone can hear and we can make a recording of it. And last but not least, as Dr. Junkerman mentioned, each session, including the panels, will be videotaped and available free on Stanford iTunes U. Handy to hear it again, or if you have to miss it, or to share with others, families, and friends. To find it, you go to the Stanford homepage, the lower right-hand corner, click on Stanford on iTunes U, and you'll find your way to our recordings. These will be video recordings. One last special feature of the course, open to everyone, lunch on Tuesdays with the week's speaker. Starting next week, not tomorrow, but a week from now, we want to give you a week's head start, a week's notice, heads up, I should say. Starting next week on Tuesday at noon on 9:30 with Dr. Jeannie Scott. It's a brown bag occasion. It's bring your own everything. The location is right next to Memorial Church in the Quad, Building 50. That's my home department, room 51A. It's the conference room. Sign up a week ahead, please. So sign up tonight at the end of class for Tuesday noon of next week to meet with Jeannie Scott, to ask all of those questions you'd like of a person who really specializes in the history of evolution and religion tension. There'll be 30 places at lunch, so please don't sign up for a second lunch until everyone's had a chance, and then we'll open it up for everybody once again, okay? So there'll be lunches every Tuesday. Bring your own sandwich and whatever you want. One last reminder, please, each week, as a courtesy to everyone, as you consider your cells and look down inside your cells, you'll remember there's an itty-bitty phone in there. We ask you to please turn off your cell phones or set them to vibrate, but do leave the mitochondria running, which provide the energy to keep those cells going. Now for the good stuff. Professor Bob Siegel will jump up here now and talk about Darwin's own evolution, background on the history of Charles Robert Darwin. Bob is one of human biology's most fabled and most highly respected professors. Just try to get into his course on humans and viruses. People line up for days to try and get in. I'll be back after Bob on the topic of Darwin's data. We'll form a panel with tonight's discussant, Dr. Lynn Rothschild, research scientist in NASA's Astrobiology Institute at the Ames Research Center, where evolution informs her work. And then we'll turn to your questions for the panel of the three of us. So, with no further ado, I turn things over to Bob Siegel.
Okay, I'm going to talk a little bit about Darwin evolving and some perspectives on Chuck E. D. Now, in the struggle for existence, you don't want to be sandwiched between Bill Durham. But I'm going to give this a try. And I want to also begin with a little pee to the speakers of this course. I'm really looking forward to hearing them. This is an amazing course, both because of you guys as the audience, because of the organizing committee, because of my fellow speakers, and because of Charles. So I'm going to spend most of the rest of the time giving a pee to Darwin. Now, in a way, this is a class with an attitude. And the reason for that is we're actually going to promote the idea that Darwin had a really great idea and that it really affected the way that people think about the world. So we have a perspective here. But I'm actually going to try to promulgate and remind you about the love in evolution. Okay. So I want to begin with my first goal, which is why Darwin? Why is Darwin such a great topic for study? Now, I didn't know he was going to show that slide, but I'm going to begin with a number of different things. I'm going to talk about he's a great topic for study because of his idea, because of the man himself, because of the record that he left, and because of his legacy. Now, there's a number of questions. What exactly was this idea? And we're going to spend the whole course actually exploring that topic. Was it really a great idea? Was it controversial? Why is it so hard to see before he made the statement about the evolution by natural selection? And why is it so easy to see now? So the central idea is essentially the origin of species by natural selection. Here's my next slide. Let's see. And we can break this down into a number of different parts. I'm going to break it down. Yikes. I'm going to break it down into 3 parts here. There we go. Let's see. And we're going to talk about species change. And they don't just change in a random way. They actually change in a way that they become more fit for their environment. They evolve. And Darwin proposed also the mechanism by which they evolved, and he said the mechanism is actually natural selection. So here's Charles Darwin sliding into third with the realization that the fittest survive. And I took a line from Bill's syllabus. It is said that Charles Darwin's theory of evolution by natural selection is the single best idea ever. This course is to find out why. Okay, so this is from a book that was developed as a result of a group that puts on a Darwin Day celebration every year. So this idea was actually promulgated in the book that was published in 150 years ago on the origin of species. And the original title was actually the succinct on the origin of species by means of natural selection of the preservation of favored races in the struggle for life. So we usually know this as... Okay, so what did Darwin do? Darwin provided compelling evidence. Darwin compellingly combined evolution with a mechanism. And we're going to talk about the fact that the idea of evolution was actually floating around before Darwin wrote The Origin of Species. He also provided a unifying principle of biology. He provided a massive body of evidence in favor of this theory. And he produced a remarkable written record, both of his thinking patterns and also of his entire life. Now, I would like to propose the idea that what Darwin really did was take an idea that was floating around and formulate it in a different way than had been thought about up until that point. So he actually resulted in a paradigm shift. And I want to give you some examples of a paradigm shift, and I'm going to make an analogy here. Some examples of paradigm shifts are the idea of the double helix, promulgated by Watson and Crick, the idea of continental drift. We all looked at maps when we were kids and thought the continents fit together very well, but it wasn't until the 70s that somebody actually decided that continents move around. The idea of natural selection and the idea of PCR. In each one of these cases, after the idea was proposed, everybody said, well, that's obvious. Why didn't we think of that? So I'm going to actually talk a little bit about the double helix of Watson and Crick. Now, what did Watson and Crick discover? Now, most people think Watson and Crick discovered DNA. Well, actually, DNA was discovered in 1869, right around the time of Darwin, by Friedrich Miescher. The actual chemical nature of DNA was discovered in 1919 by Phobos Levine. The actual structure of the molecule as a long chain, the idea that DNA was the evolutionary principle was discovered in 1943 by Avery, McLeod, and McCarty, and they won the Nobel Prize for that. In 1952, the actual structure of the nucleic acid molecule was resolved by Alexander Todd, who also won the Nobel Prize, and he did his work in 1952. In 1953, and this is actually Alexander Todd's model showing you the sugar phosphate backbone that's characteristic of DNA. Most people think that this is what Watson and Crick did. What Watson and Crick actually did was something that was very subtle. They took 2 of these chains and they laid them side by side, and they formed a helix together. And here you see them. And what happened when they did that was everything became clear in terms of how this molecule could actually replicate. And they wrote a 3-page paper, which subsequently resulted in their receipt of the Nobel Prize, although it was 13 years later. Now, this is Watson and Crick in 1953, and here we see Watson and Crick possibly evolving. This is 40 years later. Their suits evolved. Okay, so what they did was they put these 2 molecules together in a way that they wrapped around each other in this double helix. And that provided a mechanism that people instantly thought of in terms of how they could replicate. Now, it started out as a theory about the way things work, but now there's an accumulation of evidence, a preponderance of evidence, so it's no longer a theory. It actually is we think of this as a fact. Watson actually describes this story in the double helix book very entertaining. And just to show you that while it was a theory, we now have the resolution with the most powerful microscopes that we can actually see the double helix wrapped around in this braided pattern that you see over here, I guess, there. And this is a close-up, and you can see how it weaves in and out. So something that starts out as a theory can end up as factual information. And this picture is really remarkable. On the right side is a model. Actually, on the left side, I guess. On the left side is a model, and on the right side is actually an electron micrograph, and you can see the resolution down to the level of individual atoms. So again, we went from theory to fact. And they actually get commemorated by the British. Here we have on the 50th anniversary, they get the 2-pound coin, and you can see the double helix on the coin there. Okay. Now, when Watson and Crick proposed their idea, there was still residual problems of a mechanism. How could the strands be pulled apart and replicate? Well, it turns out that subsequent research showed how that can happen, and we now understand that mechanism very clearly. Okay, so what did Darwin do? Darwin essentially did a similar thing. He changed our concept of the world in what appeared to be a subtle way, but suddenly many, many things became clear. And essentially what he did is he changed the nature of scientific inquiry. Now, there were problems with his theory, and there was debate over the mechanism, and he actually had trouble with the mechanism. But what remained since Darwin proposed this 150 years ago was this change in the nature of scientific inquiry, and it's never gone back. We've continued to explore the natural world in a way that Darwin opened up for us. Honors paid to Darwin at his funeral liberally acknowledged his important role in constructing the modern frame of mind. So more than this idea of natural selection, of evolution by natural selection, is the idea that we can use empiric evidence to explore the natural world, and that we don't have to resort to principles that are found in religious texts. So basically, there is a confrontation in many cases between what Darwin proposed and religious ideology. And when I first read Janet Brown's latest book, I was thinking it's a pretty objective account. I went back and I saw that, no, actually, there's many, many references to this conflict. You know, is it apes or angels kind of thing? And you realize that this is, people in this field are indoctrinated. Now, there were some problems with the theory when he proposed it. One of the problems was a problem of complexity. How do you evolve something like an eye? Another was, where is the source of variability coming from in these organisms? Why is there no mixing? If you take two different things and two different traits and you put them together, how is it that the trait still seems to remain somehow in the organism? And he never really came to grips with the origin of life. Now, it turns out the origin of complexity he confronted head on in a very effective manner. So people are still confronting this, but actually Darwin did a great job in The Origin of Species of dealing with this problem. The other three problems he never actually managed to deal with, but many of these problems have subsequently been addressed. And certainly the idea of the sources of variability. With reference to DNA, we understand that changes in the sequence of letters result in the sources of variability, and it also explains why we have this lack of mixing, because basically traits can be carried on a chromosome from your mother and a chromosome from your father. Okay, so why study Darwin? First of all, we talked about the idea, but I actually want to bring up the point that Bill mentioned, and it's not just an idea, it's many ideas. Darwin was extremely fruitful throughout his life in a wide variety of fields, and so to just talk about his contribution in terms of a mechanism for evolution would be limiting. The next, okay, and here we see the evolutionary report card, and we have peacocks, plumage, A+, thumbs, D-, creative writing, B. Badgers, protectiveness of young, A. Ability to live in forests, A. Ability to live in newly built shopping malls, F. Humans, exoskeleton, F. Plays well with others, C. Sandwiches. Okay. So now we want to talk about why Darwin, and here we have Darwin. Darwin actually, at least this Darwin, has been around the world. Actually, like the other Darwin, he's visited all of the sub-equatorial continents except for Antarctica. Okay, but here he is. He's catching up on some reading by Niles Eldredge, who's going to be another one of our speakers. And this shows you, again, a theme that, that Bill brought up, and it's comparing Darwin with Lincoln. They were born on exactly the same day, and as one of the members of the audience said, that Lincoln was the emancipator of the slaves and Darwin was the emancipator of the human mind. So that's Bob Stevens. And this is actually what you see here is Darwin carved into a matchstick. Okay, so if you want to come, you can see that. This guy, is artisan in Santiago did that in about 15 minutes. And you can see he's actually holding the Origin of Species in his hand. Okay, and here we see both Darwins, and now they're actually consulting with Richard Dawkins here. Okay, so Darwin the man, he left a vast written record. There's a lot of unusual features that would make him good for study, even if he hadn't come up with a great idea. He sat on his theory for 20 years. He was obsessive compulsive regarding his writing, and we'll have a little bit more to say about that later on. He was accused of expropriating ideas from others, and there are actually interesting passages which that actually look very similar between some of the writings of his grandfather and himself, down to individual examples of, for instance, fighting cocks with spurs in a similar passage. So that's a debate. He spent 8 years dissecting and studying barnacles, cirripedia. He wrote books on orchids, climbing vines, carnivorous plant, that should be plants, lots of cool stuff. His last great treatise was on earthworms. Okay, so he married his first cousin, but then again, so did Freud, and so did Einstein. He played 2 games of backgammon every night with his wife and kept a running total of wins and losses. He had 10 kids. Here are his 10 kids. The number 2 is actually starred because that was his daughter who died at the age of 10, his first daughter, and it's said that he really lost his faith in God, that somehow something so horrible could happen to this beautiful child. He didn't present his first natural selection paper. He actually let somebody else present it for him. He didn't attend his father's funeral or his daughter's. He wouldn't travel to Oxford to get an honorary doctorate. He was actually sort of pretty much of a homebody. He never left the island after returning from his 5 years on the Beagle. He obsessed over his health. Actually, there's a lot of stuff on Darwin that's published. This is actually unpublished. This is a photocopy directly from the record that's actually kept at Down House where he lived. And this is his Journal of Health. And I thought I would actually make some interesting analyses of these because of my background in medicine, but it turns out it's completely illegible. But it's got like, how did you do today? Very well. How'd you sleep? Pretty good. So he kept this every single day of his life. Okay, so that's what you see here. And so this is. But even though he was very analytical, he never applied his analytical skills to his own illness. So he never figured out exactly what are the variables that led to his illness. He was a proponent of a health strategy called hydropathy, which involved drenching himself with cold sheets of water and sticking his feet in ice baths. He didn't label which island the famous finches came from, which came to be a big problem for him. So he was meticulous about some things, but one of the things that really mattered, he didn't think was very important. He traveled on the Beagle as the captain's companion. He saved the captain's life. Okay, now last year I actually took a group of students, 15 students, to England on a Darwin safari. And when I told people I was going on a Darwin safari, they said, "Oh, so you went to the Galapagos?" And I said, "No, we didn't go to the Galapagos." And so I just want to give you a little perspective. Darwin lived about 7,981 days. That's including leap days. The voyage of the Beagle was around 1,741 days. And the Galapagos was 35 days. So it was 2% of the voyage, and it was 0.4% of his entire life. So people, all they think about is that Darwin spent his whole life in the Galapagos. Well, he did very important work that you'll hear about very shortly in the Galapagos, but it was only a very small part of his life. Okay, so I want to give you some paradigms for thinking about Darwin and approaching the rest of the course. First, you could think about a temporal paradigm, what happened at different phases of his life. You can think about a conflict resolution paradigm, how different things arose and how they were resolved in his life. Convergence of factors paradigm, were the conditions ripe for coming up with this theory? And an intellectual milieu paradigm. And England at that time was a very, very interesting place. Now I'm going to just talk for a minute about the temporal paradigm as an example of how you could think about Darwin's life. And I've basically broken down Darwin's life into 4 phases: before the Beagle, aboard the Beagle, before he wrote The Origin, and after The Origin. You see they break down pretty evenly except for aboard the Beagle. And you could also look at turning points in his life, and between each of those events was a turning point, which is a very brief period of time in which a decision had to be made. So before the Beagle, he was given an offer to sail on the Beagle. It was a very serendipitous series of events that led to this, and his decision and his opportunity to go really changed his life. Then, when he arrived home, he had to set up his new life and think about what he was going to do. And then there was another turning point, was the publication of The Origin, which he brooded over for many years. And again, there was a turning point that happened in the form of receiving a letter from Alfred Russel Wallace with essentially the same theory, pretty much full-blown. So the idea that if Darwin hadn't thought of this theory, nobody would have ever come up with it is wrong, because it was actually in the air. Okay, so what about this written record I've alluded to? He left a vast written record. This says, "Not very good, Mr. Darwin, but perhaps your writing will improve gradually over time." So his published works included a series of books. I'll just put some of these down here, including his 2-volume monograph on barnacles, Cirripedia, and this included every known barnacle, both existing or fossilized. You also have his account of his trip on the Beagle, the voyage of the Beagle. You have The Origin of Species and some other books here. So I just focusing in on Cirripedia was sort of, he was very methodical. I like to think of him as Encyclo cirripedic. And then more books later in his life. He wrote on emotions in man and animals. He wrote on insectivorous plants, movement in plants. And of course, he ended up with his treatise on earthworms. His vast written record includes published books and articles. Those are just the books. His complete works, in terms of his books, are in the public domain. So anybody can read them, anybody can publish them. There are multiple editions of each one. Dozens of notebooks and extraneous notes, 14,500 extant letters to 2,000 different people on a wide variety of subjects. These are available online through the Darwin Correspondence Project, and you can search them and look for different topics, and there's thousands of books written about Darwin. This is actually the website for the Darwin Correspondence Project, where you can do research. If you have an idea about Darwin and you want to see who said what about him, you can go right online there and find out. Okay, so a number of questions might be raised. Can we know history? People are going to talk about what Darwin did and when he did it. How can we study history? How can we decide between disparate ideas? Or can we, and how can we? So one way is that there's this vast written record, and so that provides some clue as to what was going on in Darwin's life. So where to start? It's pretty daunting to think about all these resources that are available to you. So I like to begin with The Voyage of the Beagle. And The Voyage of the Beagle is actually a wonderful work. It shows Darwin's mind as a young man and how curious he was about everything in the world. And I've actually set one of the passages to verse. You can do this in a number of places, but this is a good example of how this book reads. The roar which the Maypoo made as it rushed over the great rounded fragments were like that of the sea amidst the din of rushing waters. The noise from the stones as they rattle one over another were most distinctly audible. Even at a distance, the rattling noise, night and day, may be heard along the whole course of the torrent. The sound spoke eloquently to the geologist, to the thousands and thousands of stones which, striking against each other, made the one dull, uniform sound, were all hurrying in one direction. It was like thinking on time, where the minute now glides past is irrevocable. So it was with these stones. The ocean is their eternity, and each note of that wild music told of one more step towards their destiny. So the writing is really beautiful, and it actually formed a tradition that he was quite aware of Alexander von Humboldt, who had written a book about his travels in the equatorial regions. And when he finally wrote this book, it was a big hit. He was actually quite well known and well regarded as a result of, as an adventurer, which is something in our long list of things we don't often put down there. Now, the next place to go in terms of accessibility might be Charles Darwin's autobiography. And here's a quote from his autobiography, and he is quoting his father in this quote. It says, "To my deep mortification, my father once said to me, 'You care for nothing but shooting dogs and rat catching, and you will be a disgrace to your family, to yourself and all your family.'" So this is from the autobiography. Now, this quote is in every single biography about Darwin. Now this quote, and he goes on to say, and some people have used this quote to say his father was a tyrant. Other people have used this quote to say, the next quote, which comes along, to say that it's not really true. He says, "But my father, who was the kindest man I ever knew, and whose memory I love with all my heart, must have been angry and somewhat unjust when he used such words." But here's the thing. I am not sure that this is accurate, because he's actually looking back 50 years on his life. So I actually wrote to several people and said the following thing. There are a number of off-quoted passages from Darwin's autobiography, including purported quotes from other people. These passages are believed to provide insight into Darwin's nature and character. My question is whether or not there's any evidence from contemporary letters, etc., that his father actually said this or anything like this. Or is it possible that this is just an elder Darwin reflecting back on the evidence on events from a half a century earlier, and was therefore deeply colored by time, memory, and Darwin's sense of how he wanted to be remembered? Now, I got a response back from Janet Brown, who said there's no independent evidence other than these comments from Dee's autobiography, but she goes on to say she thinks it's true anyway. I also got a comment from the person who was the head of the Darwin Correspondence Project, and he says, "I believe the autobiography is the only source we have for that statement, and many others. I think they're accurate." Okay, I'm dubious about the accuracy 50 years backwards. Okay, and to give you an example of how calculating Darwin is, I'm going to give you another example, which we actually know quite a bit about because the evidence is still present, and that's the episode of deciding whether or not to marry. Now, after he came back from the Beagle, he had a turning point crisis, what to do with his life, and so he decided he would actually analyze whether or not it was time for him to get married. So this is actually a scribble. It's not coming out very well on the screen here, but it's actually a scribble, sort of a back of the envelope calculation. On one side, on the column, on the right it says marry, and on the column left it says not marry. And he goes through a list of arguments of whether or not he should marry. And the last thing he comes to is the conclusion that he should marry QED. This is a calculating individual, okay? This is in his 20s, okay? So he was very conscious of how the world saw him and how he wanted to be remembered. Now, the third place to look is obviously his masterwork, which is The Origin of Species. And again, the final quote from this book is again beautiful, and I put it into verse. "There's grandeur in this view of life with its several powers, having originally breathed into few forms or into one, and that whilst this planet has gone on cycling according to the fixed laws of gravity, from so simple a beginning, endless forms, most beautiful and most wonderful, have been and are being evolved." And that's actually the only place where the word evolution is used in the first version of The Origin. Now, let's talk about the legacy. Now, one thing is that the ideas, as we said, have become very important in terms of how we think about the world. And here we see Darwin. He's on the 10-pound note. DNA only got on the 2-pound coin. And this has become more valuable over time, as you know. Okay, so I like to think of Darwin as a lens for thinking about the world. And because he's got these 14,000 letters, he has something to say about everything that you can think of. Okay, the next thing I want to talk about is what led to his theory, why Darwin. Now, I'm just going to put a couple of these factors out there and not go into them in detail so that you can explore these on your own. But if you've ever played the game of 10 adjectives to think about a person, there's lots of adjectives that immediately come to mind for Darwin. And as you read, you should make your own list of adjectives. Patient, inquisitive, highly critical, persistent, congenial, interested in nature, broadly interested in everything, shy, calculating, meticulous. Okay, so now here's his own assessment of what made him a good scientist. Therefore, my successes as a man of science, whatever they may be amounted to, has been determined, as far as I can judge, by complex and diversified mental qualities and conditions. Of these, the most important have been the love of science, unbounded patience in long reflecting over any subject, industry in observing and collecting facts, and a fair share of invention as well as of common sense. So that's actually a quote from him. So then we could also ask, how was Darwin affected by his times? What role did England play? What role did the Beagle play? And Bill is going to talk at length about what role the Beagle played, and particularly the Galapagos. It turns out that he was a very lucky guy in terms of having an intellectual legacy. I have a book here. This is called The Lunar Men, 5 Friends Whose Curiosity Changed the World. And it turns out these are people like Matthew Bolton, Josiah Wedgwood, Erasmus Darwin, Joseph Priestley. It turns out 2 of the 5 were his grandparents. Okay, so he came from very good stock. He had a supportive family, economic means. He never had to work a day in his life. That made it very easy for him to work with diligence on the topics of interest. He had social position, he had time, he had books and resources. Books were expensive in those days. He had access to experts. He was tireless in terms of asking questions to everybody. That's why the rationale for sending off my emails to those experts was Darwin would have done it. And very importantly, and Bill's going to talk a little bit about this, he had advocates. So he didn't even have to present his theory of evolution by natural selection when it was first presented to the Linnaean Society, because he had friends who were going to do it for him. He had broad-ranging experiences, the Beagle, and he had a lot of luck. And the role of serendipity in people's lives is extremely important. Darwin states that the voyage of the Beagle has been by far the most important event in my life, and has determined my whole career, yet it depended on so small a circumstance as my uncle's offering to drive me 30 miles to Shrewsbury, which few uncles would have done, and on such a trifle as the shape of my nose. Okay. And as you read, you'll understand more about Darwin's nose. Okay, so why Darwin? It's social milieu, financial independence. His illness may actually have contributed to his ability to write, because he was focused on his projects, and you'll hear a lot more about his illness. He was sick most of his life and his social class. The times were amazing. There were scientific discoveries of fossils, embryology. The Industrial Revolution was going on. Okay, now I want to go into a couple of traps and just provide you with a framework for things to think about during the course. And these are mostly semantic and conceptual traps, according to Bob. Now, this may lead for some debate afterwards, but the first is evolution is a theory. You hear this all the time. Now, evolution was a theory when Darwin proposed it, but now the abundance of evidence has been produced over time that evolution is a lot more than a theory. And a lot of scientists have rationalized this by saying scientists think of a theory in different ways than the general public. And I think that's a mistake. I think we should think of it, and here's an example of theories. Okay, should we teach both theories? Let the kids decide. Chemistry, alchemy, phrenology, neurology, magic equals MC squared, astrology, astronomy. Okay, so evolution, the conceptual trap is evolution evolution is a theory. Evolution is actually a unifying principle of biology. It's one of the most important things in terms of understanding the natural world. It's also very important in terms of generating experiments, and it turns out that people have thought about little ways in which Darwin was wrong, punctuated equilibrium, or they've had to modify kinship selection. And I will propose to you that although these provide fodder for the critics, the religious critics of evolution, those are actually the exceptions that prove the rule. They show the essence of why evolution is so important. And the people who propose those are actually the strongest proponents of evolution. Do you believe in evolution? As long as it's between consenting adults. So the second conceptual and semantic trap is that Darwinism equals evolution. Now, Darwin formed his theory 150 years ago. The whole notion of evolution has evolved greatly since then. And so when people talk about trying to figure out mistakes that were in the origin of species, I think it's not that fruitful. In addition, evolution was already in the air. There were a number of people who had published on evolution. In the third edition of The Origin of Species, Darwin actually includes a history of evolutionary thought and talks about dozens of other people that are actually published on theories of evolution. And here's kind of a Lamarckian view of evolution. So the dinosaur is eating the tree gets tall so the dinosaur can't eat it, and then the dinosaur gets a long neck. And so the idea that by desire you can change your physical characteristics was actually a theory of evolution that involved a type of natural selection. It turns out it was wrong, but it wasn't the theory of evolution by natural selection. Okay, the next idea, the conceptual trap, is Darwin made no mistakes. Darwin made lots of mistakes, and this is actually a quote from me, but Darwin was a moving target. A failure to understand that way is a failure to understand the man and the nature of the science that he represents. Okay, so Darwin actually wrote 6 editions of The Origin of Species. He wrote 3 editions of The Voyage of the Beagle. Here are the various editions of The Origin of Species. And this is a very interesting chart. This shows you the 6 editions, and it shows you the percent of changes in each edition. So in the first edition, he changed 7% of the book. Second edition, third edition is 14%. Fourth edition is 21%, 29%, and then 29% again in the 6th edition. So you see, he was actually modifying his theory all the time. Now, he did 6 editions in 23 years. That's an edition every 4.33 years. He would actually be currently working on his 41st edition of the Origin of Species, and I can assure you it would have a lot of stuff about DNA in it, and replication, and microRNAs, and things like that. So what Darwin did not do is he did not understand inheritance. He did not explain the process of speciation. He made an attempt at it. But since he didn't understand chromosomes, it would have been difficult. He didn't he didn't introduce the concept of evolution. That had already been introduced by other people, such as Lamarck. He didn't fully distance himself from Lamarck. He said, natural selection is the main mechanism, but I'm going to provide some room for Lamarck also. He didn't supply an immutable paradigm. Question, did he ever develop a sense of humor? There's a few passages about his nose, but other than that, it's not too funny. And he never talked to the Darwin's legacy class. Okay. A next conceptual trap is the idea that Darwin developed his ideas de novo. Again, evolution was in the air. Now, here are some quotes. These are actually quotes in verse. They're quite interesting. Creation of the earth and life. Ere time began, from flaming chaos hurled, rose bright spheres which form the circling world. Earths from each sun with quick explosions burst, and second planets issued from the first. Then, whilst the sea at their coeval birth, surge after surge involved the shoreless earth. Nursed by warm sunbeams and primeval caves, organic life began beneath the waves. So this sounds like the beginning of life and the beginning of evolution. First heat from chemical dissolution springs and gives to matter its eccentric wings. With strong repulsion into parts the exploding mass, melts into lymph or kindles into gas. Attraction next, as earth or air subsides, the ponderous atoms from the light divides. Approaching parts with quick embrace combines, swells into spheres and lengthens into lines, and quick contractions with ethereal flame lights into life the fiber-woven frame, clearly DNA. Hence, without parent, by spontaneous birth, rise the first specks of animated earth. From nature's womb, the plant or insect swims and buds or breathes with microscopic limbs. So this is the formation from inorganic matter into life. Organic life, breathed beneath the shoreless waves, was born and nursed into ocean's pearly caves. First forms minute, unseen by spheric glass, that's a microscope, move on the mud or pierce the watery mass. Then, as successive generations bloom, new powers acquire and greater limbs assume, whence countless groups of vegetation spring and breathing realms of fin and feet and wings. So we've gone all the way from the formation of the earth to the creation of organic life into microscopic forms and into the macroscopic forms. And does anybody know where this is from? I can't actually see you, but okay. This was actually written by his grandfather. His grandfather died before he was born. This was published posthumously in 1803. The full title of this book was The Temple of Nature, or The Origin of Society. And he wrote multiple tomes, all in rhymed couplets. Okay, so this was just one of many. It discusses the origin of life from its beginning as a microscopic organism through the development into humans and into society. So a very far-reaching person. Now, Darwin, in his autobiography, states, "At this time, I admired greatly the Zoonomia." That was the previous book that his grandfather had written. But on reading it a second time after an interval of 10 or 15 years, I was much disappointed. The proposition of it should be the proportion of speculation being so large to the facts given. So he basically dismissed his grandfather's work, but he was quite obsessed with his grandfather. And in fact, his very first species notebook, the first thing he wrote in it was Zoonomia. Okay, so Zoonomia, closer look. One historian of science has said Erasmus Darwin presented in Zoonomia the first modern statement of a complete system of evolution based on scientific knowledge. So just so you know that Darwin wasn't the first person to come up with evolution. And actually, his grandfather is a great subject in itself. In Zoonomia, this is on the section on generation, actually states that all animals, therefore I contend, have a similar cause of their organization originating from a single living filament, DNA obviously, imbued indeed with different kinds of irritabilities and sensibilities or of animal appendages which exist in every gland and every moving organ of the body, and are as essential to living organization as the chemical affinities are to certain combinations of inanimate matter. So in fact, he was closer to figuring out how the mechanism of inheritance occurred than Darwin was. So this is again from Erasmus Darwin. And he writes in his autobiography, I had read Zoonomia of my grandfather in which similar views are maintained, but without producing any effect on me. Clearly that's not true. Nevertheless, it's probable that the hearing rather early in my life such views maintained and praised may have favored my upholding them under a different form in the Origin of Species. So that's Charles Darwin. And similarities between Charles Darwin and Erasmus, many of them can be made. This is actually a quote from Darwin. He says, as we have been considering here how much or how little the same tastes or dispositions prevail in a family, I may be permitted to add that from my earliest days, I had the strongest desire to collect objects of natural history and this was certainly innate or spontaneous, being probably inherited from my grandfather. Okay, and he became obsessed with his grandfather, and he actually wrote a biography of his grandfather. And when I took my students to England, my most remarkable moment, which I'll remember forever, was I was actually sitting with his great-grandson in his study, and he was showing me some of the objects that he had, and I'm very interested in his biography of his grandfather. So I saw a first edition on the wall, and I pulled it down off the shelf, and I looked at it, and inside was an inscription from Darwin to Eddie, his daughter, and I showed that to Richard Keynes, his great-grandson. He said, oh, I didn't know I had that. So a priceless work. So, And let's see. Okay. Now, oh, that's not right. So I want to thank you all, and I hope you keep evolving during this course. So thank you very much.
Thank you, Bob, for that delightful and wide-ranging introduction to the life and thoughts of Charles Darwin. We're now on to part 2. Are you ready? Are you really ready? If so, then we're going to let the presentation begin. This time, the second presentation here is a presentation, as you can see, of just a small twig, a small bit of bark from one Nazca booby to the other in the Galapagos Islands. The interesting thing is that it's not at all related to the nest. The nest is a simple guano ring sitting out on the bare rock. No twig, no branch, no fluff, no twigs. The Nazca booby is one of 3 boobies in the Galapagos. Of course, there's the famous blue-footed booby. Their specialty is that foot-lifting dance where they just show each other their feet, hour after hour, day after day, male to female, female to male, back and forth. Blue-footed boobies also do presentations. You can see there's a bit of twigs here, and the other mate's looking for stuff here. Back and forth, they'll pass them to each other, back and forth, and they'll honk and they'll holler, and they'll have a good time. Sky pointing. Feathers go back, beak goes up. Both sexes will do it, one to the other. The nest again, a guano ring on the ground. Adult boobies obtain food by plunge diving for fish, and in the case of the blue-footed boobies, it's easy to see them because they're inshore feeders. They fold their wings up and they actually go in like a dart, pop back up like a cork because their bones are so light from flight. The Nazca boobies feed further out in open sea. So we have the Nazca booby, we have the blue-footed booby, and we would be remiss if we did not include the red-footed booby of Galapagos. The red-footed booby also does the sky pointing, but note this time, most precariously, it's up in a tree. Fortunately, they have prehensile bright red feet. Unlike the others, they can grasp and hold on to the branches and do that sky pointing quite famously up there in the trees. They are pelagic fishers, which means they go way out to sea, much further than the other 2 species, open sea far from land. The twigs in this case are a functional present because they make their nests in the trees, not in the ground. And so you see that we have with the boobies variations on a theme. We have red, white, and blue, very conveniently. We have tree nesters, deep sea feeders, 1 egg in the nest. I didn't show that, but take my word for it. Ground nesters, intermediate feeders, 2 eggs in the nest. Ground nesters, inshore feeders, 3 eggs in the nest. And yet such similarity in shape and form, even in behavior. With such similarity, could they be related? This is the kind of question that we turn to in part 2 tonight and think about Darwin's data. As we think about Darwin's data, I'm going to emphasize the Galapagos, as Bob mentioned to you. I'm going to emphasize the Galapagos both because we haven't done the Voyage of the Beagle yet. I guess next year I could do a better job of the whole set of Darwin's data. But in fact, the Galapagos is very important to Darwin, as we'll see momentarily. So let me use the booby's beak to draw attention to my goals for the night. First, to highlight the role of empirical data and observation behind Darwin's discovery. Darwin was an astute observer and made wonderful observations, facilitated by point number 2. I want to argue that Darwin had 3 key impulses that worked with this key power of observation: to collect, to jot notes, and to ask the why question over and over and over. And I would also like to show that 1 and 2, the empirical data and observation, with the 3 impulses to collect, jot notes, and ask why, were not enough. Darwin needed the help of experts, so that's where we're headed in part 2 tonight. Along the way, as we fly our way out to Galapagos and look at Darwin's data, I'd like to clarify the meaning of some keywords, evolution and natural selection. Bob did a great job of describing, the Darwin's discovery of these concepts, but let's put a little meat behind them. and showcase along the way some amazing local adaptations of the fauna of Galapagos. So here are the beautiful islands as seen by the space shuttle. 13 major islands out there in the middle of the Pacific with a total land area about the size of Delaware. The Galapagos archipelago is just straddling the equator. It's a province of Ecuador. It actually has an Ecuadorian governor. 600 miles straight west of the mainland as the finch flies or the mockingbird straight out from Ecuador, 600 miles, 1,000 kilometers. Straddling the equator, and as it turns out, it's in a churn of currents, very important because it made each separate island isolated from the others. The currents were very important in the isolating effect of distance in the Galapagos. The Galapagos played a very special role in Darwin's thinking. We know this from, again, his written notes, and we also know it from his own statements. Now, Darwin kept many notebooks. You'll see several of them as I work our way along tonight. But the one I like the best has this passage in it, and it's from his personal notebook. It's like the fabled note to self. Darwin would say, oh, note to self, da-da-da-da-da, and he kept this personal notebook going through almost all his entire adult life. If you flip to page 13, you can see all of this online. You can get this quote yourself online from the personal notebook, 1838, page 13. It says, in July, I opened the first notebook on the transmutation of species. This is the idea that species were not fixed and immutable, but changed over time, as Bob was reviewing, that had been greatly struck from about the month of the previous March on the character of South American fossils and species on the Galapagos archipelago. These facts origin, especially the latter, of all my views. So what Darwin is doing is looking back over the voyage of the Beagle, and as he's working somewhat surreptitiously on the idea of evolution by natural selection, he's saying the South American fossils and the species on the Galapagos archipelago, especially the latter, are the origin of all these views he was working on. We think of Darwin as a kind of a stodgy old guy in his later years. Darwin was 22 when the Beagle set sail, and I want to think about Darwin here as that young adventuresome lad who went off on the Beagle, promised for a 2-year voyage, and it turned into 5 years by the time they returned. Well, it's lucky for science that it did. The reason was Fitzroy was intent on, Captain Fitzroy, the captain of the Beagle, was intent on exacting measurements of the coastlines of South America. He actually made the Beagle go back and forth a number of times to get even better measurements and so on along the way. And the result was Darwin, with a proclivity to seasickness, would get off every time he could. So by the time they reached the Galapagos Islands in the 4th year of the voyage, Darwin had the best prep course you can imagine in the flora and fauna of South America. He'd seen much of what the continent had to offer, at least on its coastlines. Imagine a 4-year prep course on any subject when you come out to the Galapagos Islands. You're very prepared for appreciating what you find there. They spent 5 weeks exploring the Galapagos Islands, exactly this time of the year, mid-September to mid-October. Darwin, the young lad, was expecting a tropical paradise, a Tahiti, a rich vegetation, lush tropical world, and in fact arrives to a sparse desert community full of reptiles. Darwin was a bit disappointed that these tropical islands were so sparsely, aridly inhabited. He talked about the smell and the unpleasant odors of the place. Well, he had seen tortoises of the genus Geochelone on the mainland. And here's a good mainland tortoise, about the size of an American football. He got to Galapagos, and the same genus looked like this. Well, Darwin wasn't sure that these hadn't been introduced by buccaneers, a point to which we'll return, but he was fascinated by the size of the tortoises. To give you a sense of the scale, a toenail here is about 1.5 inches to 2 inches. These are big. It takes 6 or 8 seamen to lift one up and carry it off to the hold of the ship, where they turn it upside down and keep it for food. The largest herbivore of the Galapagos, it has another curious feature, the shape of the shell. The different islands have different shell shapes. Darwin was told this by the governor and gave very little credibility or importance to it, actually, while he was in the Galapagos. But if we take a look at just G and K there, what you'll notice is a very different appearance of the two shells. There's the very classic dome-shaped carapace, or shell, on the back of this tortoise, where the carapace comes right down to the neck. On this one, which we call the saddleback carapace, you'll see there's a big opening, and the carapace is flat across the top with lots of space for the upturned neck. We realize today that the dome-shaped tortoises are found on the higher islands in Galapagos, where there's more interception of clouds and therefore more moisture and more vegetation. So food is abundant. Craning your neck has no particular advantage. You go about your business eating on the ground. The dome is the shape of the carapace on these islands. On the low, dry islands, vegetation is sparse. Indeed, like Bob suggested with the Lamarckian diagram, there's a kind of a race of a Darwinian sort. The vegetation evolves to outreach the tortoise. The tortoise's carapace evolves to give them greater reach. And you see the outcome of this is that there's an upturned saddlebacking of the carapace. Well, we do regard saddleback shape today as an adaptation for facilitating the browsing at higher reaches of vegetation. You can get there with the dome, but it takes a little help from your friends. And of course, that's not very reliable. The other thing that leads us to suggest that the saddleback is the adaptation rather than the dome is that all the young are born with dome-shaped carapaces, and the saddling only shows up after age 5. On his prep course aboard the Beagle, Darwin had also seen green iguanas on the mainland, these famous herbivorous arboreal creatures climbing up into trees and using that snout to pinch off leaves and make their dinner. But he was poorly prepared for iguanas like these, the famous iguana, land iguana on the left, and the Galapagos marine iguana on the right. Darwin immediately noticed that instead of eating just ordinary leaves, indeed there were few leaves to eat, that the land iguana, the so-called conolophus or cone nose, focused on cactus pads and used that jutting jaw to reach inside and pull out the succulent material between the spines and the external hard outer edge of the cactus, for which its cone-shaped nose came in very handy. In contrast, Darwin noted that the marine iguana had a very blunt nose with the name given to it of Amblyrhynchus, which means simply blunt nose, and it is a seaweed eater. Imagine that. You arrive in Galapagos and what you think of as leaf-eating iguanas are sitting there eating seaweed or eating cactus pads. In this case, you can see a very flattened front end. It almost looks like it's smiling at you, and you can see what a contrast it makes with the cone-shaped front end of the conolophus, the land iguana. The marine iguanas are also amazing swimmers. Now, you can throw a green iguana in the water, and it will find its way across a stream using an undulating motion of the tail. But the marine iguanas are great swimmers. They're right out there with the ships in the port cities of Galapagos and so on. They feed in tide pools. They actually crash out through the surf. And Darwin noted that their tails appropriately matched their foraging habits, that the marine iguana had a flatter tail at the same size, scaled for size and so on, and the land iguana had the rounded tail reminiscent of the green iguanas of the mainland. The marine iguanas, with a belly full of seaweed, of sea algae, come ashore and soak up the sun to warm back up. They've been plunging in the Humboldt Current, which is a very cold water. And Darwin was the first to notice what he called an affinity between the organisms of Galapagos and those of South America. Iguana here, iguana there, but with a twist. But with a twist, the ones of Galapagos are bizarre. Well, why are they so bizarre? Why are they so different from the green iguana that they go swimming through the surf? Home of the world's only nocturnal gull, the swallowtail gull. The world's only found in Galapagos, and the famous brightly colored Sally Lightfoot crabs. These are the kinds of observations Darwin made, but he was most especially impressed by these otherwise fairly drab birds. Darwin looked at the mockingbirds of the mainland of South America and noticed that they had an eye stripe and a kind of a bare chest. When he got to Galapagos, he noticed that the eye stripe was there, but now they were kind of speckled, if you will, on the chest. The first mockingbird specimen he took, he used his famous technique of shotgun blasting to collect these birds. He'd learned taxidermy in Edinburgh as a student in medicine. I guess that's the one thing he carried on from his studies in Edinburgh that stayed with him, and he was able to save the specimens. He picked up a second species, what we call today the Galapagos mockingbird over on Albemarle, which is Isabella Island. He picked up a third, and so on, and we still have Darwin's stuffed mockingbirds arranged here from east to west, and you can simply note the variation in the form and coloration on the chest particularly. It's not entirely easy to see it here, but there is quite a bit of variation. He also noted the variation in these guys, the ground finches. These are the sort of finches that crawl around on the substrate in Galapagos and feed on small seeds. They're small, medium, and large, not because of the size of the bird so much as the ratio of the beak to the size of the skull. And you can see the large ground finch has a chopper on it that would be the same as if our mouths went from our chin to the top of our forehead. That's a big mouth. Beak size and shape are adapted to specific food items, and when you're in the Galapagos, you'll notice that the large ground finches eat large seeds or many seeds or both. They just chomp away. Here's one that's doing its thing with a couple in its mouth. The small ground finch, meanwhile, goes after the small seeds, by and large, and has a heck of a time with those big ones. But every once in a while, you'll find a medium ground finch or someone else with a seed just way too big to enable it to do the job. Consider now another group of finches in the Galapagos, the small tree finch. It's exciting to report that this photograph didn't exist 10 days ago. This is from our most recent trip. Boy, what wonderful luck you have sometimes, when you're just in the right place at the right time, face to face with a small tree finch who proceeds to say, let me show you how we use the beak of a tree finch. We use the beak of a tree finch to pull off the bark, to reach inside with our probing beak rather than our crushing beak, and we pull out an insect grub as quick as you please. That was about 1.5 seconds, maybe 2 seconds in the time sequence of that series of photographs. There's the medium tree finch, found only on one island. There's the large tree finch. But another fabulous sighting from this particular expedition, again, 10 days ago, this picture did not exist. This is the famous woodpecker finch. Now, there are no woodpeckers in Galapagos. Indeed, there are only a few woody species of tree. What's interesting about this is that this finch uses its beak all right to get food all right, but it uses a tool in its beak almost on every occasion to pull out food. Well, you look at that tool it's got and you say, come on, you're kidding. You should have done a better job in selecting your instrument. Boy, were we in for a surprise. You see, the classic woodpecker finch, for example, in this Darwin Foundation Strategic Plan report, they were just illustrating it with one of the wonderful curiosities of the finches in Galapagos, uses a sharp spine, and you can see how it would dig out a grub using that sharp spine. Well, here we had this big long thing hanging from this woodpecker finch's mouth. Well, little did we realize the target was also big and deep. So in it goes, and in it goes, until it is almost entirely inside. And of course, the target, what you're after, is a grub. Well, we did not see a grub produced. This whole thing, again, happened in about 1.5 seconds or 2 seconds, maybe 3. But what's so fascinating to me is that peculiar piece, if you look at it closely, turns out to be a branch of cat's claw that is being used in exactly the right direction if there were a grub to grab it and pull it out. Now that is remarkable animal behavior, using not just a stick, but a stick with thorns curved in the direction for easy insertion and for quick removal of that grub. There's also the vegetarian finch, which munched away an entire plant bud, tree bud, as we watched. In short, in the Galapagos, observations of this kind of data impressed Darwin with 3 particular observations. First, the basic similarity or affinity, as I call it, or as he called it, as I pointed out, the basic affinity of organisms in the Galapagos and mainland South America. Tortoises here, tortoises out on the islands. Iguanas on the mainland, iguanas out on the islands. Mockingbird on the mainland, mockingbirds out on the islands. A basic affinity. Parallel features in clearly different species who look related. The boobies look related, different features. The iguanas look related, but very different features. And finally, the morphological variation within his collections, especially in the mockingbirds. Darwin was to remain a creationist throughout the Beagle voyage. He was persuaded of evolution only a year later back in England. How do we know? From the work of this fine fellow, many of you know him, or some of you know him, Frank Sulloway, personal friend, historian of science. Frank has conducted detailed analysis of Darwin's notebooks. And one of them I'll just signal is the 1982 paper in the Journal of the History of Biology. So Frank looks at a passage like this, and he says, this is Darwin's ornithological notes from the Beagle, and he says, this is a really interesting place here. He's saying, for such facts undermine, inserts would, the stability of species. We understand from this passage that it's Darwin's first inkling that species might change over time, and it came not from the finches but from the mockingbirds. The full passage reads, "When I see these islands in sight of each other and possessed of but a scanty stock of animals, tenanted by these birds, but slightly differing in structure and filling the same place in nature, I must suspect they are only varieties." So he picks up these different specimens. He carefully preserves them, and he says, they must be just varieties. The only fact of a similar kind of which I'm aware is the constant asserted difference between the wolf-like fox of the East Falklands and the West Falkland Islands. If there's the slightest foundation for these remarks, the zoology of archipelagos will be well worth examining, for such facts undermine the stability of species. No, it can't be. And he goes back and he puts in a caret and the word would. We know that this happened a year or so, 8 or 9 months after the Galapagos, not in the Galapagos. There was no eureka moment. There was no, wow, these mockingbirds are fabulously different. I wonder if they're different species. No, I think they're only varieties, because boy, this would really upset things if they were different species. How do we know the date on this? Well, Darwin was a terrible speller. Frank has made a thorough examination of Darwin, couldn't spell Pacific for anything. Occasion had sometimes 2 C's, 2 S's, all over the place. Darwin was in the Galapagos. We know the dates of that. Well, when he wrote this passage, he was into the 2S and the FICK version of Pacific. So we know it was written 8 or 9 months after he was in the Galapagos. Why the delay? Why didn't Darwin get that eureka experience with all this striking data? All these finches, all the different beaks, the food specializations of the iguanas, the different carapaces of the tortoises. Why did it take so long? Darwin's original specimen list hints at some of the reasons. This is a fascinating page again from Sulloway, 1982. What it shows you is basically Darwin collected, just like Noah did on the ark, a male and female adult of each type. So welcome to the Beagle, come ashore, come with me, a male and female of each. But in addition, he lists here on this page, it's clearly here's the mockingbirds and so on. He's coming down through a bunch of birds and he starts the finch list here. And just above the finches, he lists a little female wren. Down at the bottom of the finch list, he lists a blackbird, Ictimus. Obviously, Darwin needed some help when you look at this list. He looked at this little bird and he said, well, I'll call it a wren. Because back in England, look how similar that looks to an English wren. Wow, I'd do the same thing. It's a warbler finch. We know it to be one of the finches, and it took an expert back in England to figure that out. The Icterus he had on his list, the blackbird, looks a lot like an English blackbird, if you scale it for size and so on. Whoops. Turns out it's a cactus-eating finch. It's the cactus finch. What's interesting is that these were easy mistakes to make at the time, but look what happened. Darwin correctly identified as finches only 6 of what later proved to be 13. So he didn't even realize the importance of the data he'd collected because he put labels on them that allowed him to set them aside and not wonder so much. The mockingbirds made him wonder, but not the finches. He also thought the Galapagos tortoises were not endemic, or at least he worried that they were not endemic, but introduced as food by buccaneers from the Indian Ocean. And as Bob has already mentioned, Darwin neglected to note the island location for the finches. It never occurred to him that flying organisms could be impeded in crossing by strong winds and strong currents these short distances. He did note the location for his plants, and the plants were to save the day in an important sense. The beagle returned to England in 1936, and Darwin turned his specimens over to experts for help. He turned the plants over to Joseph Hooker with all the destinations, all the locations noted on them. He turned over to John Gould his sack of carefully stuffed birds, and he turned over to Richard Owen, who was later to become an arch-enemy, the fossil mammals that he'd collected, and asked for help in each case. Let's focus just on Gould for a minute, because the story is so fascinating there. Gould took a look at the finches. Here are the finch specimens. Darwin did his best later to guess which island they had been found on, and it was all guesswork, so it was terribly done. But the important thing is this piece of paper. This piece of paper turned up in Darwin's notes in the Cambridge Library, and it's labeled Galapagos in Darwin's handwriting. You can plainly see the word Galapagos. It lists bird species. You can pick those out. So that says common noddy. You'll see a lot of common noddies in Galapagos. Here's a flamingo. You can see that Gould is saying, wow, you got a new one there, Charles. You got a new one here. You got some new species that we haven't seen before. It's clearly notes from the conversation, probably recorded live, right, just as they're working their way down this bag of specimens. And here's the interesting part over here in the corner. If we turn it right side up, 13 new species labeled 1 through 13, all assigned to the same genus, Geospiza, but 4 groups of them. Turns out this is the little wren, the warbler finch. These are the ground finches. Here are the cactus finches, and here are the tree finches. Gould could look at the specimens in Darwin's bag, mislabeled and misinterpreted by Darwin. This is what an expert can do. He'd studied finches his whole life, and he could say that these were 13 different species. Well, quickly Darwin could grasp so much diversity side by side out in the middle of nowhere in this tiny archipelago, all in the same genus, and so much diversity, greater than you'll see in certainly the size of Delaware anywhere else in South America. Could they have sprung from a common source? Darwin was later to write, seeing this gradation and diversity of structure in one small, intimately related group of birds, one might really fancy that one species had been taken and modified for different ends. Taken and modified for different ends. This is what we now recognize as a statement about evolutionary relationship. Start with an ancestral species A, time is passing. Over time, somehow, modified for different ends, you form the Bs, and somehow modified again, you come up with the Cs, so that today's closely related species C have evolved through these intermediates back from a common ancestor. We therefore use Darwin's own word, descent with modification, for this process, and that's really what evolution means. However we draw it, with time running down, where it looks like roots, or time going up, where it looks like branches, it always has a branching structure, it always has divergence. It is descent with modification, a branching pattern of life. The similarities shown by the related species are called homologous features, and the boobies are full of these, as we saw from the beginning, features that we might call examples of similarity by descent. The color, the nesting locations, and so on, similarity by descent, but with differences, variations on the theme of homology. Another major insight followed soon after this idea of descent with modification. Darwin began to draw a tree, explicitly a tree, for this pattern of life. The first tree of life diagram was in his notebook B in 1837. He said, let me start with one species here and imagine that it is modified for different ends. Aha, if it were modified like this, if there were descent with modification for different ends, genera would be formed bearing relation. This is the pattern that Bob had on his t-shirt. This is the famous first tree of life diagram. What's so fascinating about this is just a few thoughts later, 7 pages later in the same notebook, Darwin writes, heaven knows whether this agrees with nature. Cuidado. Be careful, my friend. Be careful, because this is a very important idea. And if you're not right about it, you better know what you're talking about before you put it out there. Well, Darwin was right. The finches are all related by descent. Genera are formed by descent, bearing relation. And one of the great places to see that is in the finches as they've been studied in terms of their careful DNA analysis. All the ground finch group, the finches that I showed you, cluster together, as do the tree finch group. They all cluster together. And so we understand that these are genera formed by descent, bearing relation. Darwin's view of life is then a branching tree. New species always come from pre-existing species back to the first. Species can and do change and morph, as we would say today, over time. The prevailing theory at the time, the special creation theory, had no such change in its branches. It didn't have branches at all. All species had supernatural origin during the 7 days of creation, at least according to the Genesis account of creation. They had existed in fixed and immutable form from the moment of creation right on up to the present time, unless they happen to go extinct, and you'll see there are a few extinctions in this candelabra-like view. Here, species have unchanging essences. There is no descent with modification. There is simply continuity or extinction. As Bob mentioned, other people were onto this idea, including Darwin's grandfather, but the Swiss paleontologist Louis Agassiz hinted at descent relations among fishes, showing, a convergence here back, possibly pointing to a common ancestor. But notice he never quite drew the connection. So why do we remember Darwin and not Agassiz if Agassiz was hinting at this? Well, number one, because he didn't really draw the connection. He hinted at it, but didn't draw it. But number two, he didn't draw all of the fishes linked together. Darwin went so far as to say probably all the organic beings which have ever lived on this earth. This is in 1859. All the organic beings which have ever lived on this earth have descended from some one primordial form into which life was first breathed. How did he do that? We would say the statement today that organic evolution is simply the proposition that all organisms on planet Earth are related by descent, and Darwin was the first to say that. Today we think there's good evidence leading all the way back, take all the plants, all the animals, the fungi, and so on, trace it back to a universal ancestor. How did Darwin ever get that right? How did Darwin ever imagine that all of life was related by descent without genetics, without DNA? I think the secret was Linnaeus, who in the 1700s had proposed a big system for life, organizing into kingdoms, phylums, classes, orders, families, genera, and species. Linnaeus had said life is organized, folks. It forms a branching hierarchy on the basis of observable properties. It's a natural system, said Linnaeus. Darwin said, thank you, Caroli. Thank you for that. Because the way you would get that is by descent with modification. A branching tree of life can explain, the most recent branch will give you the genera, a little farther back will give you families, orders, classes, and so on. The natural system of taxonomic classification is founded on descent with modification. In other words, Darwin says, I can explain by this simple diagram the entire hierarchical classification from Linnaeus. An interesting wrinkle to finish. This relationship of descent with modification characterizes other things. Languages descend with modification. Here's a family tree of Indo-European showing the branches that have descended with modification through common ancestors to the present day. We speak of the evolution of Darwinism. Bob has alluded to this. Evolutionary theory and thinking have changed greatly since Darwin's day. An analyst even proposed the historical evolution of helmet design from the first helmet up to the helmets more recently, showing a branching tree pattern for helmets. And of course, we have our Darwin on your bumper, the plastic fish evolve. You can see the Darwin branch up the middle. You can see sushi and fish and chips. And you can see the truth eating Darwin in the upper left. So Galapagos led Darwin to evolution. The data were critically important of the archipelago. What caused the modification? How had organisms changed over time? Darwin had the idea of change long before he knew what caused it. He had no mechanism. He just inferred descent with modification and couldn't say what caused the modification at first. A mechanism occurred to him in due course, but not because of Galapagos. because he became a pigeon breeder like his mother before him. He had the feeling that you could draw an analogy between the effect of breeders on breeding stock and the effect of nature on natural organisms. The work of breeders suggested that organisms change over time by the steady accumulation of slight successive changes that occur naturally. Darwin said, aha, nature will do this as well. From a common ancestor, all the pigeon breeders had bred these great variety of pigeons, and they all had the simple property that if you cross them again, it reverts very close to the common ancestor. If you cross any across this wheel, they revert to their progeny look very much like the ancestor. Darwin deduced that breeders selected for distinctive traits giving rise to these breeds, but they were all related by descent. The dachshund's a little better example. It's since Darwin, but you can see what's happened. A self-respecting dog was selected for shorter and shorter legs and a longer body. Darwin's epiphany on how to figure out what in nature plays the role of the plant breeders came while reading Thomas Malthus. He said in October of 1838, I read for amusement Malthus on population, and because of my travels, I was well prepared to appreciate the struggle for existence. I mean, the Galapagos Islands, the desert environment, is definitely a struggle for existence, which everywhere goes on from long continued observation of the habits of animals and plants. It at once struck me that under these circumstances, favorable variations would tend to be preserved and unfavorable ones would be destroyed. The result would be the formation of new species. Here I had a theory with which to work. We can ask in nature what causes the steady accumulation of slight changes. Darwin said it was a struggle for existence, especially in a volcanic desert like Galapagos. There are these heritable spontaneous changes. Today we would call them mutations. And Darwin thought, look, heritable slight changes that help in the struggle will be preserved if they confer simply a survival and reproductive advantage. And here he had it, because the process is automatic. Beneficial slight changes will be preserved through their survival and reproductive advantage. They inevitably will increase in proportion. Hence, we conclude that what Darwin called natural selection, the preservation, simple preservation by survival and reproductive advantage under the existing environmental conditions. That is the most succinct definition of natural selection that we've come up with. It's a completely natural force. It does give direction to organisms. It can give great design to organisms, but there's nothing supernatural about it. The preserved features are called adaptations to the local environment. So in short, my point tonight has been the data from the Beagle voyage, especially the Galapagos, were crucial to Darwin's discovery of evolution. His proclivity to collect, to write down notes, even if he didn't realize the importance with the flying finches, he did write down in the sessile plants, he did take notes where they came from that proved to be crucial, and ask why in every step. Darwin remained a believer in special creation all through the Beagle voyage, but with the help of experts like John Gould, he was persuaded of evolutionary novelty out there in the Galapagos. So we have three definitions to end with. Evolution is descent with modification, always involving branches. Natural selection, the preservation by survival and reproductive advantages, given variation, selected over time through its survival and reproductive benefit, can give you a dark peccary from a light one. And finally, adaptation, features that contribute to survival and reproduction, which we call their function, and have evolved by natural selection for those functions. So what I hope to have done tonight then is to show you how Darwin's data shaped his thinking and have given us the fundamental ideas and conceptual tools of evolutionary thought that remain valid today. Without a trip to the Galapagos, without the voyage of a beagle, even if it was just 0.4% of Darwin's life, I would argue that he wouldn't have been able to think through all the parts of the theory that are laid out before us so nicely in his reflections back on Galapagos. Great. We turn it now over to Lynn, who's with us, who will come up now. Bob, you want to come on up, and we'll sit at the table and do a panel discussion. We look forward to your questions.
I think I was initially a discussant, but I think I've become the nightcap. So if you'll bear with me for a moment, I think it was my prerogative to make some comments on the previous speakers, and they really were so beautifully done that I hesitate to do that except to say that one of my really famous and favorite Darwin quotes was not mentioned, and so at least I get to be the first one to mention it this quarter. One of the reasons I think Darwin is so appealing to many people is because you can find mirrors into your own life, particularly when things are going bad, into Darwin's life and feel maybe that all is not lost, a little bit like Einstein not doing too well in math when he was a kid. I teach astrobiology and space exploration here in the winter quarter, and so this is the one that I think my students like the most. That's sort of the winter quarter is about when you're running out of money from your parents. And this is out of Darwin's autobiography. He said, "I'd been rather extravagant at Cambridge, and to console my father said that I should be deuced clever to spend more than my allowance whilst on board the Beagle." But he answered with a smile, "But they all tell me you are very clever." And so I think that certainly applies to Stanford students as well. The reason I know this is true, Bob, is because I actually knew Darwin. He was a nice guy. I'm a lot older than you think, which is, one of the beauties of being an evolutionary biologist. You stay well preserved. Anyway, I also couldn't resist the fact that, bragging rights, Bill, that you were in the Galapagos 2 weeks ago, and I'd like to point out in this very public forum that I've never been to the Galapagos, so if you ever need a body, I offer my body to science here. However, this is me this morning. I had a crew in from Discovery Television doing a special on life in extreme environments and what that means for life in the solar system and so on. And I realized that this really was very much part of their shtick too, and so I managed to talk them into having a little bit on Darwin. So what I did want to do is take just a few minutes to talk about Darwin's legacy in the 21st century. We've talked a lot tonight about history, so I want to now take it out into what Darwin's going to mean in the future, and then the rest of the quarter will really be filling in the two bookends of that. As Bill mentioned this morning, earlier, that I have my day job at NASA Ames. I'm sorry, I was up in front of the television cameras at 8 this morning, so I'm a little shell-shocked at this time of day. But I do work over at NASA Ames. I'm an astrobiologist over there. But I also am fortunate enough to have a consulting professor position, also in human biology at Stanford. So people who are undergraduates in the room or graduate students, winter quarter, you could get a whole lot of astrobiology and space exploration if this sort of thing appeals to you. What I'd like to do is make the point that Darwin actually was the middle of the three great revolutions in thinking about man's place in the cosmos. The first, of course, was the Copernican revolution, started by Copernicus, Galileo, all the way to many extents through Newton. And this was more than just putting the Earth in its place as the third rock from the sun rather than the center of the solar system. That we were really nothing special in the physical world, and furthermore, that the physical world was run in a law-like manner. You didn't have a god that was in charge of gravity and a god that was in charge of celestial motion and so on. That all this could be explained by natural law. After that, you could argue that Darwin did a similar sort of thing for the natural world, for the biological world, that between the two revolutions, you sort of had a schizophrenic mindset where we had the physical world being run by nice law-like processes, but the biological world, for some odd reason, was run by special creation. And Darwin really reconciled the two so that he really breathed the element of time into Linnaeus, the sort of points that Bill was making just a few moments ago. He had the evidence for change. He talked to the pigeon breeders as well as breeding himself. He talked to the orchid breeders. He talked to breeders of anything you could imagine. He accumulated more data than you could possibly imagine, and that's what made his argument so forceful. It wasn't just a great idea. He had masses and masses and masses of data behind it. So you've got now the physical world being run by laws. You've got biology put in its proper context, and humans, of course, particularly being put in their proper context. But now there's been a whole convergence of events in the last several decades that have made some of us now start to look beyond that. And this is a field that we call astrobiology. And so I'm going to argue that this is the third great intellectual revolution. I don't see where the next one is on the horizon, but maybe there will be another one in a few decades too. Now, what I mean by that, and this is the soundbite version, is where do we come from? What is the history of life on Earth? But when you look at it from an astrobiological point of view, it takes really the Darwinian and the Copernican revolutions and melds them together. So we're no longer saying, all right, where do we come from? What was that primitive filament that gave rise to all life on Earth. But where did we come from, meaning where did our solar system come from? And beyond that, the stars, and beyond that, the first generation or two of stars, all the way back to the Big Bang, and possibly even the whole question of cosmology, whether we're one of many universes. We won't get into that. But how do you set the stage for life? How does it get started, and how do we get to the present? The big one that everyone's fascinated with is this whole question of, are we alone? And we'll talk about that again in a moment. And then sort of the poor sister, but in some respects the only one that's of economic interest to us, is what's going to happen in the future. We've talked a lot about the element of time and coming to the present in terms of the diversity of species, the diversity of planets, the cosmos, and so on. But all these physical laws that have brought us to where we are haven't stopped working. They still are continuing. And so there's going to be a very different sort of world in 50 years, 100 years, certainly in 1,000,000 years. We're going to have issues with the sun burning hotter and hotter. The moon is going a little bit further from the Earth every year. That actually was discovered by Francis Darwin, one of Charles Darwin's sons. And so therefore the rotational speed of the Earth is slowing down. There are all sorts of things that are continuing to happen. Of course, eventually we're going to be totally out of the habitable zone. We're going to have to move the Earth or reset the sun or do something. And actually, you laugh. I presented some of this probably 10 years ago to some entrepreneurs over at Ames, and someone came up to me at the break and said, "Should we be starting a hedge fund?" Maybe this joke isn't so funny tonight, but anyway, I'd like to sort of summarize astrobiology as Battlestar Galapagos. I think that's pretty much appropriate for tonight. And so let me just give you the few-minute boot camp version of what Darwin probably wished he had known about, where it's all led to. And of course, I'd love to think that Darwin's hovering above. I will say that with no modesty whatsoever, that I'm also a fellow of the Linnaean Society as Darwin. But you see these pictures of Darwin paper being read in the Linnaean Society. Now when you read a paper in the Linnaean Society, you have this massive portrait of Darwin standing behind you, which is rather sort of scary. So where do we come from? As I said, this is very much writ large. This is the Big Bang origin of life. And one of the big things that we've moved on to is the whole question of habitable planets. We've looked a lot at whether, of course we know the Earth is habitable, but whether other planets or moons in our own solar system are habitable, and I'll look at those in a moment. Beyond that, in the last 10 to 20 years, led primarily by Jeff Marcy at UC Berkeley, we've found many, many planets that are around stars outside of our own solar system. And we're going increasingly towards finding planets that are conceivably habitable. The problem is that with the telescopes, with the technology we have, the ones that we pick up, the low-hanging fruit, are massively hot Jupiters. So they're massively large planets that are extremely close to their parent star. So they're obviously going to be very hot, probably gaseous, and so not really a great place to live. So that's what we're seeing at the moment, but we would be very surprised if there wasn't a lot out there, and there's certainly a lot of NASA and European Space Agency missions specifically designed to look for habitable planets elsewhere. By the way, there's a running list that's kept on the Berkeley website. It was up to about 250 last I took a look. It goes up nearly every day. We have a history of impacts on the Earth. You think it was a problem when the dinosaurs went extinct with that meteorite. We've had far worse ones. The one that caused the Permian extinction was actually worse than the one at the end of the Cretaceous. And even worse than that, the ultimate bad hair day in the history of planet Earth was the impactor that hit the Earth and formed the moon about 50 million years after the Earth was formed. So we have a whole history of impacts. And what has that meant with resetting evolution? Cosmochemistry, we're discovering that there are many elements, the same sort of elements and compounds that are going to making our bodies are found actually in interstellar space. So not just water, but even amino acids and things like that. I mean, this is stunning to think that the sort of diagrams you see in a biochemistry book here at Stanford may be the same ones that students taking biochemistry around Alpha Centauri are using as well. And that, to me, it's not only depressing, but stunning. Prebiotic chemistry, we're learning an awful lot about what went into the origin of life. And the origin of life itself, which was mentioned earlier, was totally unknown to Darwin, except he proposed that it probably happened in a warm little pond, and we're actually going back to that idea again. So Darwin always resurfaces. And biogeochemistry, evolution of life, and that sort of thing is more straightforward. Are we alone? This is the sort of subject that hits the top of the newspapers all the time. And to understand this, we have to know something about the range of life on Earth, which is what I was talking about this morning. I'll go into a little bit more. What the environments are like in our solar system. So once we have some idea of the envelope of life on planet Earth, we can then look for these physical and chemical environments in our own solar system and beyond and try to map the two to get some idea where else life might be found. Extrasolar planets I've already mentioned. There's great possible habitats for life. Of course, don't want to leave out comets and so on. Many people are fascinated by the idea of intelligent life, and this is well documented by a great fascination with science fiction over the years. I personally am into the stupid life, as was pointed out to me very charitably on a panel once. I try not to think of it as stupid life. I try to think of it as smart life. I'm a microbiologist myself, and microbes are actually the ones that have the greatest diversity of environments on planet Earth by a long shot. And so between the fact that they've got the greatest diversity, and so you've got the best chance of finding them, and the fact that we have such a well-developed evolutionary theory, thanks to Darwin and all his successors, going from a microbe to, okay, intelligent life forms and so on, that it doesn't really bother me. What you really want to find is life, any kind of life, and the rest is just sort of working out the details. And biomarkers again. What I was saying before is that we now know of, well, this slide was from last March, 228 exoplanets, last April, excuse me. Probably many more are now known. We're going to see more and more and more. That number is going to go up very rapidly. These environmental extremes, this is sort of the only biology slide I'm going to show, but I have to do that. I'm a biologist. The sort of things we're talking about that would just stagger your imagination are temperature. We know of organisms that live well below zero centigrade. I mean, anyone who's seen the March of the Penguins knows that intuitively. But many microbes are even active at a point where their bodies should be frozen solid, and yet somehow they beat the odds. At the other extreme, there are organisms that can live above the boiling temperature of water. And I would love to take hours to go into great detail about those. It's just amazing how organisms are able to beat these odds. pH, this is the scale where you see acidity at the very low end and you see alkalinity at the high end. We live in a world in our cells that's just about pH 7, it's neutral. The oceans today are just over pH 8. Yet there are organisms that can live down to pH 0. I'm quite sure we will find ones below 0. Actually, some of the lowest pH ones in the world have been found in acid mine tailings in California. At the other extreme, I'm off to Africa in a few weeks, where they're the highest pH lakes in the world. They're lakes up at pH 12.5, and yet there are plenty of flamingos, cyanobacteria, all sorts of things living in there. It's absolutely stunning, the range that life can deal with. Radiation, which is what I focus on a lot, both ionizing radiation, solar radiation, and this has certainly changed through time on planet Earth. But we actually are very sensitive compared to what some organisms can withstand. Oxygen. Now, you may think of oxygen as a great thing, and it certainly is, but it's also a dangerous thing. You're literally playing with fire if you're living in an aerobic world the way all of us do. We have all sorts of redundant systems in our bodies to protect ourselves from oxygen radicals. So I'm going to argue that even oxygen, you can see those two fine young people, no relation of mine, taking in that oxygen, and they're well equipped to dealing with it. They did not keel over dead after I took this picture. We're all highly evolved to deal with this very high level of oxygen. We should pat ourselves in the back. Desiccation, being able to deal without water or very, very low levels of water. Since our bodies are basically aqueous chemistry, that's an amazing extreme as well. Organisms that can live in very high salt. I'm sure everyone here is flowing over the San Francisco Bay and you've seen the red ponds of the Cargill Salt Company. They're red because of these organisms that live at very high salt concentrations. There are organisms that can deal with very high pressure at the bottom of the ocean, or low pressure as we start to go up in space. That's a balloon program that we've been dealing with the AeroAstro department at Stanford. It's been great fun. And chemical extremes, high levels of arsenic, high levels of CO2, mercury, all sorts of things that you necessarily would not want to deal with. I certainly wouldn't want to live in those environments, but there are organisms that beat the odds and can manage. And I have to put electricity in because I personally don't want to go swimming with electric eels. This picture was also from this morning. You can see on the computer screen a little water bear. That's a tardigrade. This is the animal that can live in the greatest extremes of any animal on planet Earth. So again, it gives us an idea of what might be able to live elsewhere in our neighborhood. Well, here's our neighborhood. We can even go beyond there. And even in our local neighborhood, Venus, there's a proposal that could be life in the clouds above Venus. The surface of Venus is the hottest place in our solar system. The clouds, at some point, are cool enough and have enough water vapor that there are people who have hypothesized there could be living organisms in there. Of course, we know the Earth is fully infested. Mars, we think that there could even be extant life. Certainly, there's a good probability there's extinct life. We know there's life on spacecraft, good chance for meteors, comets. Europa, one of the little moons of Jupiter, has an ice-covered liquid water ocean. Unbelievable. It stays liquid because of tidal flexing and gravitational interaction between the moon and Jupiter. Unbelievable. This is stuff we didn't know 20 or 30 years ago. Titan around Saturn, and now little Enceladus. Titan is like a frozen chemistry lab. It's got incredible organic chemistry going on there. And so this is always a possibility for life, but it's certainly a great way to go back in time and look at what the conditions are that life could have originated under. Enceladus is another little moon around Saturn. It's really hit the news the last couple of years for astrobiologists because there was an oxygen tail coming out. And it was quickly shown that that is really the smoking gun. That's the trail suggesting that there's liquid water coming out of cold geysers in the bottom of Enceladus. And so yet another place, just when you think you know your own neighborhood, you don't even know your own family. And so we're starting here. We've got all sorts of places that map onto these physical and chemical conditions for life. There's probably much more in the universe. For the future of life, again, I mentioned the environment of the Earth is changing because the environment of our neighborhood's changing. The sun's changing, the moon's changing in relation to the Earth, and so on and so forth. Of course, the universe is going to continue to change. Everything's going to continue to change. And therefore, the solar system, unless we physically intervene, is likely to break apart. It's been a great thing for 4.6 billion years, but it's not going to be here forever. There are ideas that the universe will end someday, and others that there will be some kind of replication. We may end in freezing, bitter coldness, nothingness, or not. We may recycle. We're not going to be here to find out. That's the good news. And of course, the response of life to all this change is going to be fascinating. And I don't for one moment imagine that if the lights are turned out on planet Earth in a couple of billion years, that we're going to sit around and wait for the lights to be turned off. I firmly believe that we're going to do everything we can to stay on our mother ship. And failing that, we're going to move our home or move ourselves. And of course, we're always interested in this question of life beyond Earth. So getting back to this, the idea of astrobiology is the last revolution, a natural following from Darwin, and Copernicus before that is looking at our place in our local neighborhood and then moving on to ours as life in the solar system. And so thank you very much for letting me finish off this evening. It's going to be a great course.
Okay. The question is to elaborate on the notion of what is a theory. A theory is usually you start out with a group of facts and you try to organize them into some coherent whole that will bring meaning to those facts together. Usually, most people think about a theory as something that would be similar to a way to generate hypotheses, so you could actually look further at the issue. So hypotheses generated from a theory are often testable, and so if you generate hypotheses from a theory and begin to test them and fill in the details, then you now have something that is tantamount to a scientific fact. One thing that's nice about science is that you never quite get to truth with a capital T. You just keep working your way at it. But when things, if you talk about, for instance, the chemical nature of life, we understand it to such a great degree that there's nothing that can sort of wipe that off the chart.
I have a simple one-word contribution to make. I think of a theory as an explanation for things. I don't know if that will help.
So an explanation could be true or it could not be true. So I think that's a good way of thinking about it.
Well, the question is, why is the U.S. so low on the scale? Why are we down at that very low end in the surveys like the one for the New York Times? Certainly one reason is once the big ratchet of public education begins to slip, everything works against the knowledge in schools. Let me give you a personal example. Years ago, I was part of an effort here at Stanford to take the human biology curriculum. We start the year with evolution. Evolution is an organizing principle for the entire human biology course sequence and the whole program. And the idea was to take that curriculum and repackage it for middle school grades, 7th and 8th grade, when studies have shown there's a great loss of interest in science, that it becomes a lot of memorization and a lot of rote formulas and so on. And so we wrote a unit on evolution, carefully using dog breeders. We took the inspiration from Darwin. We decided we would use breeders as an example to smooth into the unit. Many, many teachers said they were delighted to use human biology, or hum bio as the unit was called, and afraid to use the evolution unit. That there was a fear that they would be in trouble in their communities, that they would suffer enormous parental feedback if they so much as tried to use a unit involving the E word. The unit on sexuality was fabulously successful. Sexuality was considered much less controversial in communities than evolution. So the problem is that when you get to a state in society where very few people understand evolution, people are afraid even to start talking about it. And that's the ratcheting effect. Over time, it leads to a continuous erosion. And I think we've simply neglected, for a generation or more, we've neglected the basic training in evolutionary thought.
I can add to that. The other problem is that a lot of the textbook purchasing centralized in places like Texas and California, which are huge markets. And so if there's an objection to something in those states, the rest of the country just has it left out. I'm constantly amazed by the number of students I get at Stanford who simply have never been exposed. It's been taken out of their textbooks.
I'll have to concur that the issue is a societal one and how we educate our kids. It's interesting if you look at The Origin of Species that basically you can make his entire argument without using the word evolution. So the real issue here is, are we actually teaching the children how to look at facts, how to look at information, how to critically analyze information? I think that's actually where we're falling down.
In fact, Darwin, as you pointed out, Bob, wrote that whole book using the word evolved only in the very last word of the very last sentence. Descent with modification works great, and yet we found teachers hesitant to even use that expression in schools.
In fact, there have been various, okay, can you use Darwinian natural selection at a prebiotic or origin of life level? And absolutely. In fact, there have been various NASA bureaucratic panels that have defined life as something that can undergo Darwinian selection. And so this goes back to things like looking at an RNA world. The idea is that before there were individual cells, there were self-replicating RNA molecules, and these would be competing with each other. I mean, you even see that sort of thing going on within a cell. For example, in a bacterial cell, you can get extra chromosomal circles of DNA called plasmids, and they can compete with each other. People like Richard Dawkins have talked about having genes competing with each other. So even in the subcellular level, which is analogous certainly to the prebiotic level. So yes, absolutely, competition all the way through, and natural selection.
One last question, we'll call it a night. Bob Stevens, there's a friendly face. We all seem so optimistic. What's your real assessment of where we're actually going?
Meeting adjourned.
The wonderful thing about evolutionary theory is it's post hoc. It explains the past, and it's very difficult to use to make predictions. The one prediction that you can make, I think, is that adaptability evolves. If I've learned a lesson in the Galapagos, and I've been to some places in the Galapagos that surprise you, how devastated they are by human introductions. You know, there are more species, we've introduced more species of plants in Galapagos than were there on their own. We've introduced mammals that have devastated entire island habitats and mountaintops and so on in the Galapagos. And you can, wring your hands in despair, or you can look around and see what happens when they go in and shoot out all the goats and shoot out the pigs and so on. The wonderful resilience of life. The kinds of perturbations that a humans bring to Galapagos are not new in the history of life there. There have been lava flows and El Nino events and eruptions and climate change and weather variation, and you name it, organisms are just bathed in perturbations. And so there's an adaptability about life. If I'm optimistic, it's because of that very simple adaptability. I see you clear the pigs off an island in Galapagos and the vegetation grows back. You begin to see the giant daisies coming in. And I mean, it's amazing, but that's the origin of my optimism.
Maybe I'm a little less optimistic, and I think the Galapagos example is a really good one because what it shows is that if we're proactive, we can actually make a difference. And so I think the idea is that the more proactive we are about some of these issues, the more likely it is that we are going to have a salubrious result. And I think, as you surmised, overpopulation is probably the number one issue, and people have looked at carrying capacity. Nobody really knows what the carrying capacity of the Earth is because it changes with technology, but the fact is that there is definitely a concern that we're above the carrying capacity now and that a collapse may be imminent. We may be wrong, but I think we're better off to sort of assume a worst case scenario and do something about it sooner than later.
Would you like the last word?
All right, from a long-term point of view, from an evolutionary point of view, if you look at planet Earth, a lot worse things have happened. Like I said, the moon was just a horrendous day. I mean, and the day that the dinosaurs were killed, they say they all went extinct in 20 minutes. I mean, that's got to have been one of the worst 20 minutes on the history of the Earth. I mean, nothing's, I don't care how bad it was for Bear Stearns last week. It wasn't as bad as that 20 minutes at the end of the Cretaceous, and the Permian one was even worse. I mean, the difference is, and the levels of CO2 in the atmosphere, they've been orders of magnitude higher than they are now. The only difference is we're now here and we care. So we care very much whether the oceans rise a few centimeters because Miami's in big trouble. Fortunately, we don't live in Miami, but it's in big trouble. There are a lot of places that are in big trouble from very tiny perturbation because we're here to realize it. And so that's the bad news. We're here to think about it. The good news is it's not that great a change in the history of the world, and the good news is that we're here to do something about it. And if you sit around and piss and moan, you're not going to do anything about it. So you got to be optimistic and go out there and fight.
Thank you all. We'll continue a week from tonight.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.